Welcome. This is the penultimate lecture of this course series. Today what I do is I will introduce you to another class of instability. So, we have talked about instability, but what we have really discussed in great detail is the spontaneous duetting of an ultra thin viscous liquid like film. What I discussed today is the instability, what is known as the contact instability of a soft elastic film, and also we talk about the elastic contact lithography. So, soft elastic film essentially we are talking about a thin elastomer film, and we have actually talked about an elastomer in pretty good detail while talking soft lithography. It is essentially a cross-linked PDMS is a perfect example of a elastomeric thin film. So, we have argued that this has some, unlike a polystyrene or a PMMA film, which are essentially the linear chain molecules. So, they are in a frozen in glassy state at room temperature. Okay. So, if you heat them beyond their glass transition temperature, they behave like a liquid. But this elastomeric film, the soft elastic films, they are physically cross linked actually, right. So, and this there is lot of flexibility within the matrix, this we have already argued, and PDMS as a material has a sub-zero Tg. So, it is typically liquid at room temperature. So, we have already also argued how to cross link a Silgard film and it becomes flexible, etc., etc. Typically, there are two paths. So, you can vary the proportion of the cross linker to get the or tailor the exact shear modulus of the film, and this elastic modulus you can find out from rheometric analyses to the extent of what is the storage modulus, what is the loss modulus, what is the extent of elasticity, etc. The system is very simple. So, firstly, since this molecules are cross linked, they are actually stiffer than a viscous film, and therefore, even if if you make a very thin film out of it, due to interfacial attraction, if they try to deform, the physical cross link sort of opposes in addition to the surface tension forces this deformation. So, this type of a system never exhibits a spontaneous instability. Due to attractive interfacial interaction, it never exhibits. However, what is seen that if you take such a film in close proximity to another rigid surface, okay. So, here is another rigid surface which we would be referring as the contactor. What happens is below a critical separation distance between the two. So, now instead of talking about the interaction between the two interfaces of the film as we have so far talked about, we are now talking about the interaction between the free surface of the film and another rigid contactor. Okay. So, this is the interaction we are now talking about, and when the separation distance is below a critical separation distance, what happens is there is this attractive interaction between these two destabilize the surface of this soft elastic film, resulting in some isotropic structures. Okay, so, this is the system geometry we are talking about. So, you have an elastomeric thin film and you have a rigid contactor. So, if you bring the contactor in close proximity, so below a critical separation distance, there are these self-organized structure formation on the film surface. So, the patterns essentially form due to a competition between the attractive van der Waals force acting between the free surface of the film and the contactor. So, again the van der Waals force, again the attractive van der Waals force is present, but the force is not active between the two interfaces of the film, but it is between the contactor and the film, and any instability is essentially opposed by surface tension as well as elastic forces originating from deformation of the matrix. So, what happens is now you are looking at a system. So, suppose the film evolves like this, you will immediately see. So, this is the contactor, let us say, which is coming in contact, the film becomes unstable, makes some structures which sort of tend to go and touch the contactor. Okay. But what happens is you have to understand that you are talking about a cross-linked films. So, the moment some parts of the film sort of elongate towards the contactor due to the instability, other parts try to pull it back because you have these physical crosslinks which are present. Okay, this is unlike a purely viscous system where you do not have any restoring mechanism other than the surface tension. So, once you can sort of overcome the stabilizing influence of surface tension, there is nothing to hold it back really. Okay, so this is a competition there, or in other words, there is a much stronger competition here, or much stronger restoring effect present within the film in case of an elastic film, which is in the form of the physical crosslinks of the molecule. Okay, and this competition results in the structures which are short wave structures. So, the patterns have periodicity which are much smaller as compared to the long wave approximation we have already talked about in case of debating of a thin film. So, H is much smaller than X, but that does not really happen here. There is a small, we will just give you a very brief theoretical understanding of that, but before that let us see what type of instability we are actually talking about. So, now what you are seeing is actually from the top, again under a microscope. So, you are now seeing, so here is the contactor, here is the film, and which is rigidly bonded to a substrate, and the contactor or the film is approaching towards the contactor. Okay. And you are seeing from here. So, it is possible to perform these type of experiments if you on an optical microscope platform. Only requirement is in that case the contactor has to be transparent. Okay. And here you use a transparent contactor, and the film or the contactor is progressively approaching the film. See what happens. So, as the contactor approaches the film, you see certain things are appearing, okay, and which is growing in number. So, these are some isolated columns. So, let us note down what are the things we see. First, we see some isolated columns, then we see that more columns appear. Then if you further allow the progress, you see that the columns are getting transformed into bicontinuous labyrinths. Okay. So, the next thing is you see some bicontinuous labyrinth like structures. So, here is the bicontinuous labyrinth like structures, and then if you allow approach, these labyrinths get transformed into isolated holes. which you will soon see. Yeah, now it is a stage which comprises isolated holes, the black dark spots, before the two come in complete contact. Okay. So, here is something which is again very interesting. So, let us start from the beginning again and watch the movie. So, the contactor is approaching from the top, and what you see is the appearance or the manifestation of instability is with the formation of some isolated columns, and then as it approaches further, more number of columns appear, and then suddenly you see a whole lot of structures. So, all over the film surface the structure now transforms to the bicontinuous labyrinth like structures, and on further approach these labyrinth like structures get transformed into isolated holes, and before the contactor and the film come in conformal absolute conformal contact. So, what happens here is that these structures originate, as we have already pointed out, due to a competition between the attractive van der Waals forces and the restoring effects imparted by surface tension as well as the elastic deformation. So, this is the morphological evolution sequence. So, you first the onset of instability is with the formation of columns, then more number of columns appear, the columns tend to get elongated and they gradually get transformed to these labyrinth like structures, and then it is associated with an increase in the fractional area of contact. Then you have these random bicontinuous structures, and then finally these holes. What is interesting, the basic physics of so this is what is known as elastic contact instability. And very briefly, the basic physics of elastic contact instability can be understood, that the elastic strain energy per unit area of a film surface deformation is given as U mu into H del V del X plus del U del Z whole square, where mu is the elastic modulus, H is the mean film thickness, X and Z the lateral and normal direction, and U and V are the components of displacement field in X and Z direction. They are not velocity. Okay. Now, this equation along with the continuity equation which is as well as the characteristic orders which are x is of the order of lambda, which is the natural length scale of instability, z is the order of h, the film thickness, and v is the order of delta, which is the vertical amplitude, of the pattern. Okay. So, we have this equation which gives the elastic strain energy along with the continuity equation, mu h x z and u v are defined here, and the characteristic orders again as we did an order of magnitude analysis. So, x is the order of lambda, z is the order of h, and v is of the order of delta, which is the vertical amplitude. What gives is that u, the strain energy, you get an expression like this. So, from this expression what you can see that the energy penalty for deformation, this derivation is beyond the scope of this lecture. So, there is no need for you to go into this derivation. The energy penalty for deformation increases both for very short and very long waves. Okay. So, because of the nonlinearity of the equation, so if lambda is very short or lambda is very long, both ways u sort of increases, and the minimum elastic energy pattern for which lambda will be equal to 0 has a length scale is possible only when lambda is of the order of h, or the lateral wavelength of instability, natural wavelength of instability is of the same order of h. And detailed theoretical calculations show a prefactor close to 3. So, lambda is roughly 3 times the film thickness, and this has been verified in experiments. What is more interesting is, apart from this scaling or this short wave scaling, which makes the structures really short wave as compared to the long wave structures observed in instability, there are a couple more things which are important. Firstly, what we need to understand that this form of instability is completely distinct from the instability of a purely viscous thin film we have discussed so far. First difference, we have already talked that this instability is triggered or engendered by an intersurface attractive interaction, intersurface. So, you have to have a contactor and then you have a film, and the instability results due to an attractive interaction between the contactor and the film, rather than a spontaneous instability as observed in a purely viscous liquid thin film. And the interfacial the attraction or the interactions was between the two interfaces of the film. Here the interaction is between the film air interface and the interface, the free interface of the film and the contactor. But the second more important thing is that the surface evolution in case of a duetting or a instability of a liquid thin film was associated with physical displacement of liquid from one part to the other, physically displacement of polymer by diffusion and convection. In contrast, here there is no physical flow of either by diffusion or convection of the material, and what you see is just an elastic deformation of a soft solid film. So, it is a purely elastic deformation of a soft solid film, and there is no transport of material by either convection or diffusion. Okay. The other important thing as far as the scaling, so the other thing we understand, of course, it's a short wave instability as compared to a long wave instability that is observed in case of the instability of a spontaneous instability of a liquid film. The other interesting thing is what we have seen in the video is the progressive morphological evolution during the bonding and the debonding stage. So, if you perform the opposite experiment, that is the contactor comes in complete contact and then you withdraw it again. So, the experiment we saw or the movie you saw was for the situation or the case of bonding, where the contactor was progressively approaching the film, but you can also do a debonding experiment and you see a similar morphological evolution in the inverse order. So, first from conformal contact, if you start debonding, you will first see the holes coming in, then it will be followed by the labyrinths, then the columns, and then finally it detaches. There is of course a little bit of hysteresis in terms of the vertical separation distance. So, the critical distance at which the patterns form while you are approaching, and the finally when the two surfaces debond completely, there is a difference between that, but that can be attributed to pinning of the patterns to the surface. Okay. Other interesting thing is this lambda equal to 3/8 scaling or whatever scaling is there remains valid almost across the different morphological settings. So, the columns, the labyrinths, the holes, they all follow this lambda equal to 3/8 scaling. Importantly, the scaling relation valid across morphologies and very importantly, the scaling relation is independent of the exact value of mu, exact shear modulus, as well as surface energy of the stamp. So, here also you now have a potential flexibility. So, you take films of two different thicknesses, the periodicity of the structures you will get will be different, but the morphologically the structures will be roughly the same. And the other thing is you can vary the vertical separation distance and can create either holes or holes or pillars or labyrinths. So, these are interesting aspects from the standpoint of patterning. You can see that with films of different thicknesses, if you do an H versus lambda plot, they roughly fall on the same line, irrespective of the morphologies, irrespective of the shear modulus of the film, as well as the nature of contactor. The other important thing to realize is that these structures, unlike the structures formed in duetting, where the energy sort of dissipates due to viscous dissipation and there is a permanent deformation on the film surface. So, you take a flat film, it deforms permanently, resulting in holes or droplets or whatever. In contrast, here, since the nature of the deformation on the film surface is predominantly or completely elastic, so the structures are temporary or they are not permanent. So, the moment the contactor is withdrawn, the elastic or the flexible crosslinks, the bonds present or the flexible crosslinks present within the polymer matrix restores the surface of the film, elastic film, back to its original flat morphology. So, therefore, the patterns are transient and are present only as long as the contactor, which essentially signifies the destabilizing force field is present. Okay. Once the contactor is withdrawn, the patterns again restored back to its original flat morphology. So, if you want to use this elastic contact induced instability as a viable patterning technique, one of the critical requirements will be to make these patterns permanent. Okay. And we are talking essentially of using a polydimethylsiloxane based system. So, what can be done, or what has been done, or what is typically done is, so this is how it is, the contactor approaching the film, you have a flat film. So, while as long as it is in contact proximity or in contact, you have the structures, but once the contactor is retracted, the structures go away. So, what is done is that if during this stage, while the contactor is in contact proximity with the surface, if UV is exposed, if the whole assembly is exposed to UV light, what happens is that ultraviolet irradiation produces atomic oxygen by dissociating first the atmospheric oxygen at a wavelength of 184.9 nanometer, and this this atomic oxygen again recombines with the oxygen that is available in the atmosphere to form ozone. That is why this UV exposure thing, which we have already talked while discussing about tailoring the surface energy of a PDMS film in terms of a whole lot of lithographic applications, CFL, mimic, etc., etc. Then again also we discussed it, but let me quickly repeat that. So, this UV exposure, what it does is that it breaks down the atmospheric oxygen into atomic oxygen at 184 nanometer irradiation. This atomic oxygen recombines with the molecular oxygen to form ozone, but this ozone also gets dissociated by the UV at a 253.8 nanometer or 254 nanometer irradiation. Okay. So, what you have is within the chamber you have a whole lot of atomic oxygens which are present. This atomic oxygen reacts with the siloxane film surface, and it sort of forms higher oxides of silica on the surface of the film. So, here in presence of a contactor you had a deformed film surface, and then you expose it to UV ozone. So, it forms a very stiff surface layer, okay. And this stiff surface layer So, this stiff surface layer now prevents the relaxation of the film once the contactor is withdrawn. Okay. So, thereby you can make permanent patterns on based on elastic contact instability. Of course, the making the structures permanent is associated with some chemical modification of the surface. Now, again if you look into the nature of the structures, even if you are able to make these permanent patterns by UV exposure, etc., etc., the critical issue is that you still can't use these labyrinths or hole or columns or whatever for any practical application, because they lack long range order. Okay. So, what was considered that if this elastic contact instability has to be used as a viable patterning technique, the structures arising out of elastic contact instability have to be aligned. And the simplest approach that was taken was, so this is the regular setting. So, you have an elastic film, which I am writing now as a film, you understand it is an elastic film. This is a contactor. So, the attraction between the contactor and the film, the adhesive or the attractive interaction which is responsible for the manifestation of the whole instability, is uniform between these two now in a regular case. So, instead of that, if a topographically structured contactor was taken, then what would happen? You have a film. What will happen is, because of the topographic contrast on the stamp surface, over these zones the attraction is stronger. As compared to these zones which are where the separation distance is higher. So, one can talk about a simple grating, and instead of using a flat contactor, one can approach the film with a grating, let us say. And because of the feature height or the topographic contrast on the surface of the contactor, now you have a spatial variation in intersurface separation distance, which results in a spatial variation in the extent of adhesive interaction between the film and the surface. So, what is expected? What was expected was that by using a pattern contactor, it might be possible that the zones below the stamp protrusions will preferentially become unstable and therefore result protrusions of the stamp preferentially unstable and result in aligned structures. Okay. So, this is what was expected. And then if one can make these structures permanent at this level, probably one can get aligned structures using or utilizing the concept of elastic contact instability. So, this is what schematically is shown here, and let us now try to see what exactly happens. So, this if this type of a contactor, a pattern contactor, approaches the film, it is expected that it forms, we expected, or people working on this area expected that probably a positive replica of the stamp pattern will form on the film surface. Let us see what exactly happens. So, here is a flat elastic film to which a simple grating contactor is approaching, and we will have a cartoon to over this zone to show you what exactly happens. So, as the film approaches first, it is far away, nothing happens. So, it now comes closer and below that critical separation distance. So, there is now an active interaction between the contactor and the film surface, and you see that the onset of instability here also, or let us use a fresh page. Okay. So, we are looking at the approach stage. So, the onset of instability is again with the formation of columns. Why I use the word again? Because of the fact that when we remember that when we used a flat contactor, then also the instability, the onset of the instability was with the formation of isolated columns. But what is the difference here? The key difference here is that because of the presence of the stamp protrusions or a topographically patterned stamp, the columns that appear are not random, but they are sort of aligned, and all the columns form at some zone or the other which is below a stamp protrusion. It may not be forming at all locations. So, let us say this is a stamp protrusion which you are looking at, and this is the film surface. So, this is how it goes, and somewhere or the other, so the column can form here or something like that. So, it forms only below the stamp protrusions. Okay. So, the columns forms protrusions. Okay. Therefore, the columns get aligned. You go for further approach, what happens is, because you have some columns which are probably spanning between the film surface and the stamp protrusion. So, the stamp comes down further. So, what happens, these columns sort of elongate along the stripes or the stamp stripes, as well as the reduced intersurface distance results in enhanced attraction between the stamp protrusions and the film surface. Therefore, more number of columns appear, and eventually one gets to a positive replica of the stamp. So, the question to ask is, looking at this type of a structure, how does one ascertain whether it is a positive or negative replica? Because the problem is that the duty ratio is 1 here. Okay. So, you are seeing atomic force microscope images in this particular case. So, at every stage what was done, that the patterns were frozen by UV ozone exposure, so that the stiff surface layer appears, and therefore, these structures can be made permanent, and then one investigates them. And so, what happens is that the critical question one can ask you, how do you determine, looking at a structure like this, whether it is a positive replica or a negative replica? So, let us say you know the geometry of the contactor, again from atomic force microscope, what you can find out. For this particular case, if I remember correctly, the height of the grating was 200 nanometer. But if you look at, so you have essentially reached this stage where a positive replica forms, and we expect it to be a positive replica, but then you are looking at this structure and you see it is a grating. But how do you negate? So, this would be a positive replica, but one can also argue that, well, it is not that, you have simply embossed the film, which is also possible, and you have formed a negative replica. So, this would be a negative replica. Since the periodicities are same and the duty ratio is 1, so it is very difficult to identify whether it is a positive replica or negative replica. But if you do an AFM scan and find out that the feature height, and what was found out here, that let us say the feature height was H2 and the stamp feature height was H1, or the contactor feature height, and it was seen that H2 was higher than H1. So, using a 200 nanometer using a stamp with a 200 nanometer feature height, it was possible to obtain around 400 nanometer high structures, which is never possible if a negative replica is forming. So, therefore, it has to be a positive replica. So, this way one can of course use the concept of elastic instability to generate ordered structures, and also the advantage is, unlike a soft lithography based technique, where you like embossing, where you get a negative replica, you can actually create higher aspect ratio structures. But there was more to it. So, since beyond the stage where a positive replica is formed, if the contactor was approached further, what happens is you have to understand that these structures, if they are not frozen in, they are some tall strips of polymer of this soft elastomeric material. And if you press them from the top, what will happen? There will be some sort of a bulging instability along the periphery of these polymers. So, it is something like this. This is the morphology. And then you have adjacent stripes which are now exhibiting this bulging instability. And this happens only at a stage if the contactor continues to approach beyond the stage of positive replica formation. Okay. So, beyond the stage of positive replica formation, it continues to approach, and you see some these type of bulging instabilities along the length of each of the positive replicated strips. So, now what happens, since now the additional thing that arises, now these two bulged portion from these adjacent ridges sort of start interacting with each other. So, the intersurface attractive van der Waals interaction now sets in between these two bulged portions. So, this is the film which is a positive replica has formed, and now there is an intersurface attractive interaction. So, what happens is, and this results in bridging of these bulged portions, forming a bridge like this, and therefore, this is an unique thing which is not seen in any existing soft lithography technique, that these bulges sort of bridge up in this direction also, resulting in an, so this sort of bridges up, resulting in an array of holes. So, this is a perfectly ordered 2D array of holes that result from approach or contacting an elastic film with a single 1D patterned stamp. So, this is a real unique feature of this method. These structures can be made permanent, and this whole approach, which is a patented technology now, is known as elastic contact lithography. So, there are some additional critical issues. So, further approach will eventually lead to a perfect negative replica of the stamp, which is nothing but simple embossing. There are some critical approaches. So, using a single stamp, a simple grading stamp like this, by varying the intersurface separation distance, now you have the potential of generating a variety of structures. So, aligned columns, positive replica with higher feature height as compared to the stamp, array of 2D holes, etc., etc. The important thing to note is that simply by taking a stamp and an elastic film will not give you this structure. This structure, people are working on the theoretical aspect. There is some complex bifurcation in the energy landscape which leads to this formation of 2D structure, but the issue is fully not fully resolved yet. What is important is that this ordered array of beakers or tiny holes this forms only when there is a commensuration between the lambda of the film and lambda p of the stamp. What does it mean? Suppose you have taken a film with a stamp with lambda p equal to 3 micron. What is lambda of the film? If you use a flat contactor, it is going to be 3H. This is a shortwave instability for an elastic contact lithography, elastic instability. So, if you take a film now, then only lambda becomes 3 micron. So, this statement, what this statement means, that there is a commensuration between lambda and lambda p, implies that this type of an ordered 2D structure forms from a simple 1D pattern stamp only when lambda p and lambda matches. So, in this particular case, these structures resulted in a film which had a thickness of roughly 1 micron using a stamp which was which had a thickness, which had a periodicity of 3 microns. What happens is, if there is a mismatch between these two length scales, you do not get these type of a beautifully ordered structures. For example, here is a case where the film thickness was 1.3 micron and the stamp periodicity was 3 micron. So, you see that you are still close to that formation of 2D holes, but the alignment is not that good, it is slightly distorted. Okay. However, if there is a significant difference between lambda and lambda p, for example, here the film thickness is 500 nanometer and the periodicity lambda p is 3 micron. So, in this case lambda p is 3 micron and lambda equal to 1.5 micron. So, it is roughly half. So, what you see is that a double periodic structure emerges, or in other words, this is the type of structure that forms. So, here and if you check at the periodicity of this peaks, it still is 1.5 micron. So, the signature of the information that emerges out. So, this is 3 micron, the stamp periodicity. So, this gap is roughly 1.5 micron. So, if you now look at the periodicity of this double periodic structures, what has formed over here. So, this would be the periodicity, it is roughly of the order of 1.5 micron. So, the take home message is that an elastic film even in the presence of a confining stamp or a pattern stamp, rather faithfully follows the natural instability length scale. Okay. Similarly, if you take a scenario like this, film thickness is 4.2 micron, stamp periodicity is 3 micron, it does not match. So, film thickness is much higher. So, here what will happen, the lambda corresponding to the film thickness is of the order of 13 micron and lambda p is 3 micron. So, see what type of structure has appeared. So, you see that you get a strange type of a structure where you have 3 stripes and then 1 stripe is missing. So, 3 stripes under the stamp protrusion would essentially mean so this is, let us say, the stamp, and what you see is a very interesting structure, this and this one is missing. Then again you see this, the next one is again missing. So, it continues like this. what it implies now, the periodicity of the stamp is 3 micron. So, 1, 2 and 3. So, from here to here it is actually 12 micron. Okay. And you see the natural periodicity is roughly 13 micron. So, here as if this whole individual structure now behaves as one single elastic instability structure, so that it still obeys the natural length scale of instability under this type of a situation. So, this is in a nutshell the method of elastic contact lithography. The other approach that had been taken was to, instead of using a combination. So, here in the classical sense we had a patterned stamp and a flat contactor. The other combination was to use a patterned substrate and a patterned stamp and a flat film was the condition we talked about. The other alternative would be to use a patterned substrate and a flat contactor. So, in the previous lecture we talked about using a topographically patterned substrate for spin coating or something. So, the moment you take a topographically patterned substrate, you now get a film which has undulating top surfaces. So, same thing happens here. If you now use a patterned substrate and onto which you coat your elastic film, you have an undulating film with an undulating top surface, and therefore, the intersurface separation distance over here, over these locations above the undulation, is lower as compared to other areas. So, this is expected to give some sort of a directionality, preferential directionality. And if you now do an approach sequence, you see that the morphological evolution sequence is almost the same. You again see the array of holes appearing in this case, and this optical micrograph shows how well organized and large area these structures are. So, this is the morphology of the initial film, and you need to understand that here you are using a flat contactor and a film with an undulating top surface. So, these zones you have a preferential attraction as compared to the other zones, and therefore, it results in the formation of again aligned structures using elastic instability. So, this is a level where you see. So, this is interesting in the sense that here the effect of the substrate sort of bleeds through the film and resulting in first a sort of a replica which morphologically resembles the substrate itself. This is the substrate. This is what happens when the columns form because of adhesive attraction. So, as the stamp sort of approaches, one would expect first that, so this is the substrate, and first the columns would form like this. Again, this I am not very sure whether it is a positive replica, but when you get to this stage, the height of the features is much higher than the original height of the substrate patterns, and then subsequent approach of the flat contactor again starts to the bridging, and eventually you get to this array of holes, and final before final conformal contact is achieved at resulting in a completely flat surface. Here also this commensuration between lambda and lambda p is important. So, if there is a commensuration, you get an aligned perfectly aligned array of these 2D holes. Lambda slightly lower than lambda p distorted array, lambda higher than lambda p, you tend to get back to the aligned structures, but the labyrinths, but they are sort of aligned because of the presence of the subsurface substrate, pattern substrate or aligned substrate. and when the film thickness is much higher, it completely sort of disobeys the presence of the substrate pattern, and you get these labyrinths. The other interesting aspect is that you can tailor this lambda equal to 3/8 scaling by using an elastic bilayer, where this scaling ratio now becomes Rm is a function, lambda is a function of Rf into h, and this Rf can be tailored between any values between 0.5 and 8 depending on the configuration of the elastic bilayer, and which becomes a function of the ratio of the shear moduli of the two layers as well as the thickness of the two layers. And in principle, it becomes possible to achieve a much reduced Rf. So, you can now start off with a film which is much thicker and can achieve smaller features. Recently, this concept of an elastic bilayer has also been extended with an ECL to generate sub micron lateral scale structures with elastic films. So, I think I will stop this lecture here. So, in this lecture I gave you a glimpse of a new kind of an instability, which is elastic contact instability, which is observed in elastic films in contact proximity to a contactor or a stamp. Okay, and this is induced by intersurface adhesive attraction and is opposed by the elastic restoring forces. And we have shown that how this form of instability can be used for as a viable patterning technique by combining the concepts of again a top down method like using a topographically patterned stamp or a substrate. The uniqueness of elastic contact lithography or ECL is that due to complex bifurcation in the energy scenario, it's one of the rare methods which allows you the formation of ordered 2D structures using a simple or a 1D patterned stamp. So, I think I will stop here. Thank you.